off because I didn't have time to get questions in. So, but I have your exams back to give to you at the end, all right? So I'll keep this as brief as I can so that you can take a look at those exams.
You take the quiz?
Yeah. Yeah.
No, sir.
No, I shouldn't get one ready. Shouldn't get one ready.
Oh, man. I was looking forward to the quiz.
You wanted to. Oh.
Oh, man.
My Bible, yeah. All right, so when you're looking at the learning objectives, structure and function of the cardiovascular system is an A&P component, so I'm going to go as quick as I can through that kind of information. And we'll take a look at electrocardiograms because they're really interesting, but there would not be anything on electrocardiograms in the exam, right? Because that's not a exercise physiology theory, it's just a tool we could use to look at the heart, and it's interesting to understand what it can show us if you're working with clients who have some heart issues. So this should be review. Hopefully everybody has an understanding of circulation. Right? Blood's going to come back to the heart and into the right side atria, down to the ventricle, out to the lungs, back to the left atria, left ventricle, out through the aorta to the rest of the body. Right, so make sure that you review and remind yourself of the direction of flow through the heart, because the direction of flow and the role that each chamber plays within the heart impacts what we see happen when we look at adaptations for exercise. All right? So you just have to have a good picture of which way the blood is flowing around, which part of the heart is responsible for sending it to the lungs, who's responsible for sending it out to the body, okay? When we look at the heart as a muscle, we'll mention in a little while it's slightly different to skeletal muscle, but it still requires nutrients and oxygen, right? And it's tempting, I think, sometimes to just say, well, it's full of blood, so it can just get nutrients and oxygen from the blood that's inside the heart, but that's not how it works, right? It doesn't take anything from the blood that is flowing through. All the nutrients and oxygen supply come via arteries that wrap around the outside of the muscle, right? So in particular, the coronary artery branches off of the aorta, and then it splits into right and left coronary artery. They're the largest ones. They wrap around the outside, but there's lots of these smaller arteries that wrap around and provide glucose and oxygen to the heart muscle and take away carbon dioxide. Right? Blood pressure is very high in the aorta. That's the highest point in the body. Right? And it's also, because they come directly off the aorta, blood pressure is very high in the coronary arteries. So that's a common area for disease because of the pressure levels there. And we often hear about people having to have a coronary bypass. Right? So in that case, what happens is the coronary artery gets blocked and they go in and they literally do a bypass around the blockage, another piece of the vessel that's died. Right? So that's a pretty clever way of developing, because if all these arteries and things were in the muscle or inside the heart, then when the heart is contracting, all those arteries would get closed off and we wouldn't get oxygen and nutrients, right? So having them wrapped around the outside is a very good design, because that way I still get everything I need. Anybody not recognizing anything to do with structure, direction of flow? Okay, all right, so let's look at the actual cardiac cycle. So we have contraction, relaxation, continuously right through our lives. Right? So the contraction phase is called systole, and the relaxation phase, where the heart is filling back up with blood, is called diastole. When we measure blood pressure, we have systolic pressure over diastolic pressure. Systolic is the high number, diastolic is the lower number. Right? So it makes sense that systole is the contraction. So whichever way you find the easiest to remember which way round those are. Right? And when we look at the heart, it's an interesting muscle, because we've talked about how we contract skeletal muscle. Right? There has to be a signal from the brain that comes down the motor neuron and stimulates the muscle to contract. Right? But when we look at heart muscle, it doesn't necessarily need any information from the central nervous system, because it has this intrinsic control. And we call it autorhythmicity, which is way too complicated to say on a Friday afternoon. All right, so the heart muscle is able to create its own electrical impulse and send that impulse across the surface of the muscle to get the muscle to contract. Right? So that electrical impulse starts in the back. There's a special clump of cells at the back of the right atrium called the sinoatrial node, and for short, that is the SA node. Right? So the SA node is what we call the pacemaker of the heart. Right? So it can initiate an electrical impulse, a signal, and that signal then moves across the surface of the inside of the heart muscle, and so we see a wave of contraction. If you actually watch a heart beating, the whole thing doesn't contract at the same time. Right? It's pretty simultaneous when you look at the atria. Most of the atria contracts relatively simultaneously, but there's a little bit of a wave. And that pacemaker sets the heartbeat at about 100 beats per minute. Right? So if we took away all the other influence on the heart, our resting heart rate would be about 100 beats per minute, which it clearly isn't. So we know there's something else at play. The signal travels across the surface of the right atria, and it reaches another set of specialized cells that is at the junction between the atria and the ventricle, and it's called the AV node, okay? Atrioventricular node. And the AV node has a very special job, different job to the SA node, but equally important, because the AV node hangs on to the impulse for a fraction of a second. If you think about what our structure is like, right? If my blood is coming in to the right atria, excuse me, George, I'm just gonna make sure these out here. All right. So blood comes in to the right atria. The right atria contracts, squeezes the blood into the right ventricle. Now, if the wave of contraction is simultaneous across the entire heart, then the atria and the ventricle would be contracting at the same time. Where would the blood go? Right? So, what happens is the signal gets to the AV node, and the AV node goes and hangs on to it for a second while the atria is contracting, squeezes all the blood out, and then the ventricle contracts while the atria start to relax. So actually what you get is a slight delay between the top area of the heart contracting and the bottom area of the heart, so that the blood can flow down into the ventricles. Right? If I'm pouring water out of a jug and I shut the top of the cup, where's the water going to go? Right? So I have to be able to hold open the ventricle for a little bit of time. So that's the job of the AV node. It just sits on the impulse for a tenth of a second, and then it sends the impulse off around the ventricle. And because the ventricle is relatively large, we need that impulse to travel across the whole surface at a very quick rate. And it's carried by some special branching called the Purkinje fibers. And they transmit electrical impulses very, very quickly. So that means that we don't see too much delay right down here at the bottom of the heart versus contraction at the top of the ventricle. All right, so intrinsic control of heartbeat. We don't have to have a signal from outside of the heart in order to stimulate heartbeat, contraction of the myocardium. Obviously though, we do have some external influence because we're not sitting here in class with a heartbeat of 100 beats per minute. Okay? For most of you, because you guys are fit, it's way down in the low 60s and possibly in the 50s. So how come it's that low if the pacemaker is setting it at 100 beats per minute? So what we have is the influence of our autonomic nervous system, parasympathetic and sympathetic influence. Okay? Parasympathetic, remember, is our rest and digest. Chill out. All the blood flows going to our stomach and our digestive system. We want all that nutrient from the food. Okay. Our sympathetic nervous system is our fight or flight. So now I need all that blood flow coming out to the muscles so I can run as fast or hit as hard as I need to hit. And I need that blood moving quickly because I need lots of oxygen and lots of nutrients getting to the muscles. So the sympathetic is responsible for increasing heart rate. Parasympathetic is responsible for decreasing heart rate. So while you're sitting here in class, which one is dominant? Parasympathetic, right? Because it's bringing down this impulse that's stimulated by the sinoatrial node from 100 down to 63, or whatever your resting heart rate is. Make sense? Right? So parasympathetic is dominant, and then when we turn off the parasympathetic, heart rate's going to start going up straight away because we've got the pacemaker setting a rate, and then we can turn on sympathetic and increase it way over 100 beats per minute, right? How hard is your heart working when you're out running around doing your training? Right? So mine's up around 138, 139 at the top of my training zone. Sometimes it creeps into 140s and I don't like how that feels, right? So we can make our heart rate way higher than our pacemaker is setting it when we need to. We also have some other influences from the endocrine glands, which kind of back up the sympathetic signal to the heart muscle, because the sympathetic nervous system also stimulates the endocrine glands to release adrenaline, epinephrine, and norepinephrine when we exercise or when we're under stress, right? So we also have then the action of that epinephrine on the heart muscle as well. If we train a lot, then what we get, the technical term for decreasing our heart rate is called bradycardia. So your resting heart rate is 63. That's pretty low for average. On average, an adult's heart rate is somewhere between 70 and 75, maybe even 80, depending on are they male or female, how large are they, right? The more we train, the more we see resting heart rate slow down. So training-induced bradycardia is healthy, mostly, right? The lower my resting heart rate, the healthier I am. The less chance I'm going to have high blood pressure, the less chance I'm going to develop heart disease. So on the whole, lower resting heart rate is a good thing. However, bradycardia can be pathological. So if you have someone who is overweight and sedentary, and their resting heart rate is 58, they better go see a doctor, because that would be highly unusual. Right? Highly unusual. So you want to be able to think about, why is this person's heart rate below average? Right? Is it because they're fit and healthy, or is it indicative of a problem? Okay. So technically bradycardia is anything less than 60 beats per minute. Some of you will have resting heart rates that are less than 60. Right? When I was in my 30s, mine was down around 57, but I was training harder than I do now. So if you're doing a lot of aerobic work, you may have technical bradycardia. If you're doing a lot of anaerobic work, sprinting, lifting, your heart rate is likely to be lower, but it probably isn't that low. Depends a bit on your genetics. Question?
How can smoking get you high blood pressure?
There's a couple of different reasons. When you smoke, the carbon monoxide that you take in sits on the hemoglobin and blocks the hemoglobin from picking up oxygen. So people who smoke also, after they've had a cigarette, their heart rate goes up because there's not enough oxygen in the bloodstream, and so your heart beats faster to try to deliver more oxygen.
Will working out help that or no? They just should stop smoking.
They should stop smoking. Yeah. Yeah. It's horrible. And that's without all the other stuff that's in there, you know, just the carbon monoxide.
Doesn't it depend on like what you smoke though?
Well, if you're,
Cigarettes.
yeah,
Why?
if you're smoking a nicotine-based cigarette, if you're rolling a spliff, marijuana wouldn't do that. The problem is when you roll a spliff, you use tobacco. So if you smoke a pipe, spliff,
How do you know split?
how do I know spliff? I used to spend a lot of time. No, my mum used to smoke spliff. I don't do marijuana, I stick to alcohol and marijuana are not a good mix. You usually end up with your head down the toilet. That is not a good mix.
That's like personal experience.
No. I don't go there. I stick to wine. But if you use a pipe, whatever they're called, you wouldn't get the same problem. It's not the marijuana doesn't block.
It's the
It's the carbon monoxide from the tobacco. So, yeah. Just tell anyone you know that does that to give it up. It is just horrible. It's very hard to give it up though. It is highly, highly addictive. It is really hard. My sister's on her like 5th or 6th attempt to quit smoking now. It's very difficult. Yeah.
All of this makes sense. You know, like those electrical cigarettes, like, is that the same reason why you have blood pressure as well?
No, you shouldn't because you don't actually, the electrical cigarettes are more about the habit of smoking.
Is it more nicotine?
I think they give you a little bit, but it's not the nicotine that causes the oxygen issue, it's the carbon monoxide. So,
Give you crystals.
give you crystals, electrical cigarettes.
It's water.
I heard that cocaine doesn't do that.
Yeah, the whole thing is, it's a bad habit to develop.
You can
But I can say that about drinking, but it's
have a
not.
certain amount of nicotine in it, you can choose which one you want. They go
That sounds really good.
Yeah. It's a very, very, very hard habit to break.
It's almost like half the size, but those. Yeah.
Here's the weird thing though, is that lots of athletes use cigarettes because smoking cigarettes suppresses your appetite.
Really?
So ballet dancers have historically smoked a lot because they don't want to eat very much. And so a lot of athletes use cigarettes to depress appetite. Yes. Bad stuff. Alright, so our myocardium then can obviously generate force. It's got to squeeze a lot of blood around a very large network of arteries and arterioles and capillaries and venules and veins back to the heart. So it has to do a lot of work. The more I'm working, right, the harder I'm working, the more work my heart has to do. So it can contract for a very, very long time, hopefully, otherwise we're in trouble. So what kind of muscle fiber is it more like? Type 1s, right? So it works in a much more similar way to a type 1, even though the structure is slightly different, but it contracts, it starts beating somewhere around 4 weeks after conception. Right? So, and if you're lucky enough to live into your 80s or your 90s, there was a very long time that muscle was contracting continuously all day, every day. Right? So it's very, very good at utilizing oxygen that it gets from its own blood supply. Right? It has a very high mitochondria density because it's working aerobically. So it has to provide the building place to make ATP. It has, as you saw on that picture, an extensive network of blood vessels wrapping around it to provide all this oxygen that it needs. So there's only one type. Right? Myocardium is myocardium, period. It doesn't have different subsections that we're aware of. Okay? Don't worry too much about intercalated discs, and that's more detail than we need. So the thicker the wall, the thicker the muscle, and as with skeletal muscle, more thickness, more muscle means additional force. Okay? So what I want is nice, big, fat, thick muscle in my heart. Okay? And here's our first point of importance for the flow of the system, because why would the left ventricle have a higher thickness? So when you look at a heart, the left ventricle has a much thicker wall than the right ventricle. But think about the right ventricle is sending blood to the lungs. The lungs are right here. So it doesn't have to deal with gravity, right? It doesn't have to push blood all the way down to your little toe so your little toe doesn't fall off. Okay? So the right side of the heart does significantly less work than the left side of the heart does, because the left ventricle has to push blood out through the aorta, which we said has the highest pressure in the whole system. So it's got to get the blood out of the heart against a very high pressure, and it has to contract hard enough to send that blood all the way around the body. So whenever we look at a heart, that left side is way, way stronger, bigger, fatter, heavier than the right side. Okay. Not because it's different muscle, but just because if I was doing bicep curls on one arm and not on the other arm, I would expect this arm to be bigger, fatter, stronger, right? So it's got nothing to do with a change in muscle type between the sides. It's all about how much work are they doing. So what we see in the left ventricle is that if we train regularly, whether we're doing endurance work or weight training, we see much larger left ventricular muscle. Right? It's thicker, it's heavier, it's stronger. If I am weight training, then a lot of that is because it has to work right? I've already got very high pressure in the aorta. If I'm pushing weight, blood pressure goes up even higher, as we'll see across the semester. Right? So now I've got to work even harder to get the blood out of the heart if someone is lifting. If I'm doing endurance work, then I've got to get a lot of blood out because I need a lot of oxygen and glucose over an hour and a half, 2 hours, however long you're moving for. So we also see adaptation in the muscle in the left ventricle. Right? So we see a similar adaptation regardless of which type of training. Slightly greater in the weightlifting because of the work against the pressure, but we'll come back to that idea when we're looking at adaptations. We also see that in people who have chronic hypertension, because all the time, every time the heart beats, it's having to push blood out against a much higher blood pressure in the aorta than it even is in you guys who are healthy. So people with chronic hypertension also have this thickening, this heavier left ventricle, but it's not because of healthy reasons, it's because of unhealthy reasons. So it's going to be larger for athletes, for people who train, for people who are healthy, but when we look at it in a pathological, it tends to be absolutely abnormally large. I have a story for everything. My cat has hypertrophic myopathy. So his last chest x-ray, his heart is so large that it's almost touching his rib cage either side of his little chest cavity, bless him. It's massive. Well, he should be dead by now. Yeah, he's made it. Every time I ring the vet for more meds, they're like, "You are kidding me. He's still alive. Okay, come get more meds." So he thinks he's great. He's running on the tree and chasing the birds and beating up on the other cat. But it's massive, his little heart. So hypertrophic cardiomyopathy means enlarged heart that is not due to healthful habits. Okay? So it's logical, right, that we don't see that adaptation in the right side of the heart because the right side of the heart is not having to do that amount of work. Right? So that anatomy, structure, and an understanding of that drives all these changes that we see in regards to exercise. I can run every day for an hour, and the right side will be healthier because the carotid artery will be wider and it will be delivering lots of nutrients and lots of oxygen, but I don't see a change in the weight and the size of the right ventricle. Okay. In very, very, very elite endurance athletes, there's some indication that there might be a little bit of change, but it's not a typical picture. All right, we'll stop there, we'll do exams, and we'll look at ECGs on Monday.
Scotty too high. Walk here, go high. I need to go potty.
I have not logged these, so please don't walk off with them. Make sure you give them back to me when you've had a look. Check my adding up as usual. Joe's